So this is the second class of particle in a box. And when I watched my video, I realized I spoke so quickly. I did not realize when I watched my video. Did I speak very quickly? Not think so. Okay. Probably the video has given you an impression that it's really. All right. Thank you. Okay, very good. So today we're going to go over the particle in a box, and we will go over this part. Let me just remind you what we end up with. So we already have the problem. Now we want to solve the Schrödinger. Solve time independent Schrödinger equation. So this is an eigen equation which we are going to solve. So let me check it. Okay. So this solve time dependent Schrödinger equation. We already have the equation. Let me write this down to you guys. d5 over dx squared. And we have 2me and h bar squared. We have a phi equal 0. So this is a term which we have. Last time we called this, we did not mention this terms at all. But this is a bulky, with just too many stuffs in that. So I'm going to use a simpler letter called k squared to represent this part. So make my equation looks a little bit simpler. Plus phi equal 0. So this is what we end up with, except that I'm called this per term is called k squared. And you may wonder why I called k squared, and I will explain it shortly. So for the moment, that's the equation which we have. Now, as we said last time, we're going to compare with the standard differential equation, which is we have a y double b single and c y equals 0. So we are comparing our Schrödinger equation with our ordinary differential equation like this. So essentially what we have, the solution is going to be, for our case, is going to be lambda squared plus k squared equals 0. So this is the solution we mentioned last time. Do you guys remember? So that's what we discussed last time. In other words, this guy will become lambda squared, and this guy has a lambda 0th order, so that's what my lambda is going to be. Did I explain well? In other words, this is a generic solution. You're going to have this, but for our special case, we have. Let me write a generic solution. Generic solution will be a lambda squared plus b lambda plus c equals 0. So this is the generic solution. But for our case, my a is just 1 here. There's no b term, and the c term, c is just k squared. And this phi doesn't count because it already have the order lambda. So this actual lambda 0th order, so that's what we get. So my lambda now equals plus minus I k. That's what we'll get. And then the solution for this is a generic solution for our Schrödinger equation. We have two constants with a e to the I lambda 1 x plus b e to the I lambda 2x. So this is a generic solution. Doesn't matter whether we have any kind of other properties. We always have this generic solution. So this generic solution will stay as they are. Now, did you see I have a lambda 1, lambda 2 is actually plus minus ik, so I can write it down. Let me choose lambda 1 be positive k, and let me choose the lambda 2 be negative k, so I will have this particular expression. And this is my wave function for the moment. So now, from this on, we will enforce the boundary condition. So from here to there is a boundary condition starting. And this is where physics come into play. Before this is all mathematics. There's no physics. Essentially, you have a differential equation You solve the differential equation, you get that solution. It always behaves like this. Now we're going to force the physics into it. The boundary condition at x equals 0, the wave function has to be equal to 0. Because this is a particle in a box, let me remind you, here is my x-axis, here is my y-axis, here is 0, here is a. So below x, x equals 0, it's all infinite, here is also infinite. So that's why the boundary, and this will be phi 0 equals 0. When I plug it into that, this will be phi 0 is going to a e to the 0, so this is the 1, and e to the 0 again, 1, so the b equals 0. So our first boundary condition tells us our a, b must be the same. So this means a equals minus b. So then, when I'm done with this, I can simplify my phi in the following way. My phi, new phi now, I'm going to remove this b to replace b by negative a. So this will be a e to the I kx minus e to the negative I kx. And this is the wave function I go through the physics part. So in other words, the boundary condition that I get. So I can do the calculation. This minus each other will be 2ia e to the I kx. And this is my wave function here. And in principle, I can stop here. I do not need to do anything. Now, there's another boundary condition, so which is, this is the used one, another boundary condition. Let me call the boundary condition 1, so I just 1 here. Another boundary condition, another physics portion is going to come into play. And so there's another wave function, another boundary condition which is going to be utilized here now. And this boundary condition is at the other end, which is at this location, so which is x equals a. X equals a, the wave function also has to be 0. The wave function also has to be 0 in this case. So the first wave function gives us this. Then we're going to plug that into this equation. So you see I'm going to write phi a is going to equals 2ia e to the negative k. This x becomes a now. Is going to equal 0. So I can eliminate the ia. So then I have equation ika must equal 0. So now this equation is really important. This tells us my ka cannot be chosen any arbitrary number. This k cannot be any arbitrary number. For instance, if k equals 0 here, then it won't be equal to each other. You see, if this is equals 0, e to the 0 power is 1, so it doesn't work. The only case it will survive, it must be equals n pi. So n pi is the only solution for our equation. You see, let me show you. For instance, n equals 1 when you equal 1 pi, and this you can see cosine pi and minus or plus I sine pi. So this will be, you can see in this case it's going to be 0. Oh, hold on, did I get? So this is pi. This should be 2 pi. Yeah, this should be the correct one. Yes, it is correct. It should be correct. Should be right. Yes, this is the correct. So in other words, in this case, I can always choose this particular value here. So my n here is going to be equal to 1, 2, 3, all the integer numbers here. And this is the 1. Now, once I get this, my k, in the beginning I do not have the subscript. So now my k is going to be written like this. N pi divided by a. So this is the, I should write n a little bit better. So this n pi like this. So this is essentially give us the answer for our calculation. So this is the one which we got over here. All right, so that's that pi. And oh, forgive me, I made a mistake. Folks, this part, forgive me, I now realize. Folks, this is not right. This should be cosine, forgive me. This is sine kx. This is sine kx. Again, forgive me, this should be sine kx. That's why that's incorrect. Let me change this. So these minus each other should be 2i sine kx. So here is sine, forgive me. Now ka is kx like this. Now this makes a whole lot of sense. So now if my n equals 1, this is k equals pi. Sine pi equals 0. Yes, I did not realize I made a mistake here. So this is the equation which we got over here, like this. All right. I didn't do anything except I plug in the boundary condition for the first part and determine a and b. Put another boundary condition into get this equation. And this is extremely important. This gives us a quantization condition. You remember in quantum mechanics we get on the quantized, how the quantization actually comes out is because you have a restriction on the waves. What do you mean by restriction? You see, I confine this wave into this particular narrow region. I confine that. So you know this comes from confinement. If you confine a particle such a way that it becomes so restricted, what a quantum particle does, okay, you confine me, I will become quantized. That's what it means. So that is the, if you restrict me, have confinement, and this is the quantized. And how do we know this is the actual quantized? Well, you see n is discretized now. So that's why each one label this one. Now we're going to plug this in back into our energy equation. Remember, our energy equation is 2mE divided by h bar squared. This is our definition of the k. You can see here, from here to there, it's our definition k. So this is going to equals k n squared like this, k n squared. Are you guys being able to follow? In other words, what I am doing now, I got this k, and I will want to plug that k into that equation. That's what I'm doing. So now you see, I'm going to add, watch carefully, a subscript onto my E. And this just labels such fact that the energy is quantized. So now I solve for E. So this will be h bar squared, n squared divided by 2n. And this is the energy of the particle. Here now we know kn is just a wave vector. Here is a wave vector. You can check the units immediately, and you will find the units to 1 over meters. So this is a wave vector. And this is the quantized energy. Now, if you want to write an expression directly, complete expression, you can plug this one into that equation. It's a little bit boggy here, which you don't like it, but if you wish, I can plug it in. Then n pi divided by a. And this is the quantization energy. You'll notice that this quantized energy is different from the Planck expression. You remember Planck's case, he used n equals nh mu. You remember this guy? You remember this? And this is only for the photons. This is only for the photons case. But here's for the particle. Any particle could be work like this. So they are different. In other words, you see the quantization different depending on what kind of system you have. If you have a massive particles, you will behave like this. And this turns out very, very interesting, also very valuable. Let me sketch a diagram for this energy, because this is our eigenenergy. Eventually, we got this one here. Now, in order to get eigenenergy, we are going to move on to the next portion of the class, which is over here now. The energy. I'm going to sketch a diagram. I'm assuming that my n equals 1 is this particular level. If you see n equals 1 is this particular number, let me write down to be more precise. So this will be h squared pi squared divided by 2ma. So this is my unit of that. But now as far as it goes to 2, this will be twice of this big, like this. And 3 is a whole lot larger. And these are called energy levels. These are called energy levels. You could have a whole lot more energy levels above like this. Later I will show you a real example where this actual particle in the box appears. But for the moment, let's just look at these energy levels, what do we have. So let me summarize what we got so far. We solved the Schrödinger equation, and then we got his eigenenergy. Now, what we are interested in, we move on to the wave function. These are eigenstates. And these are eigenstates. These are the wave function which we will have. Let me write down the phi here. You see my phi over here is the sine 2ia, like this, sine k. Now, for the moment, I do not have subscript. So you're going to see me write down subscript here. In other words, I'm going to write down n here. This one subscript is purposely added 2ia sine kn, purposely added. So this is my wave function. And this wave function, obviously, it's not normalized because it's not equals 1 at all. So we're going to normalize it. How do we do the normalization? What do we need to do first?
Multiply it by a constant.
Exactly. We're going to multiply by a letter c, whatever the c that is. I'm going to multiply by c. Whatever. Just multiply by c. So that's what I do. And then I will have a c, and then have another c star phi n, like this, and do the integral dx. So that's how the normalization is done. So you just essentially multiply by c in the front, whatever the function, doesn't matter, just put c in the front, and let this guy equals 1. So now I have a c phi n, and now you see, this one is a real, so it doesn't matter whether I put a star or not. So it doesn't matter. Essentially, this guy is just squared of this. Dx equals 1, like that. So that is my calculation. We plugged in this into it. So we remember we have this part will be 4a squared. Remember this complex conjugate, this I has imaginary, so it will be 4a squared, like this. And then this is going to equal from 0 to a sine squared n pi divided by a, and dx like this. So this is my integral, how large the integral this will be. And this integral is really, really straightforward. And this part just equals a over 2. And this part is just a equals a over 2. So, and then you can see the entire expression, the entire wave function expression, this equals 1. Now, folks, I'm going to call this entire things This entire thing, you remember, this entire thing is just in front of my wave function. So therefore, this entire thing is going to equal, just in my time, in other words, this, the brackets representing this part, just equals 2 over a, like that. 2 over a. So you know, this part just equals 2 over a. And then I take square root of both sides. I take square root of both sides. Yeah, that's I take square root of both sides. I take square root of both sides. And now, this term will be C4, instead of 4, just C2a like this. So C2a just equals square root, and this was square root like this. So in other words, I just multiply by this term, this particular portion. We can simply ignore I will explain shortly here. So this part is now our normalized wave function with a square root 2 over a, lowercase a, forgive me, lowercase a, and sine kn x. And this is our normalized wave function. So this normalized wave function is what we got here. So this is our normalized wave function, and now we finally got this expression. So that's how the normalized wave function looks like. And this wave function, let's just look at the I. I did not explain this I for the moment. This I doesn't matter whether we have R or not. Let me show you why this is the case. So this is our Schrödinger equation, look like this. This is our Schrödinger equation, look like this. You can see I can multiply both sides by I, both by I. So there's no effect on the energy, because you can see this term, this is completely equivalent to my following equation. It's just both sides multiplied by constant I. It doesn't matter. So these two are exactly the same. Especially in the one-dimensional case, we always choose a real wave function like this. Now let's enjoy this wave function. This wave function is very interesting. Here is my x equals a. You see in the beginning, the first wave function is just like this. This n equals 1. That's n equals 1 wave function behaves like that. But if n equals 2, this is going to be doubled in the sense like that. You have nodes on this. You see, we have a node on the top of this. You have a node like this. And this n equals 2. N equals 3 would look like this. Sorry, I cannot draw very well. Textbook mentioned very well. So this is n equals 3. So you notice that if energy is higher, you have a more oscillation is going down. So here is the generic features. The higher the energy is, the more oscillation the wave function has. So the higher the energy, you have more oscillations. So you could imagine if I have show you that graph, give you more oscillation, you know the energy will be higher. So this is a one which we have. And textbook does have this particular features, and you can see them easily. And this time, I want you guys to read it. Let's read the textbook 34 to 36. And this part, we're going to read together. Probably your textbook slightly different from my page number, and but I want to tell you what actually this is. 34. So we're going to 34 to 36. So we have page 34 to 36. And this portion is really, really interesting. Okay, we're going to go to the example 7. Folks, go to example 7. I don't know whether it's 34. Which page do you get?
34, yeah.
You have 34. What about Aisha, the 34? example 7. Example 7, like figure like this. Yeah, too much. No, you're gonna go up, go back. Further back. No, just go on the top. Keep on going. Should be your. Yes, exactly. Yeah, like that. So you see the example 7, it says completeness. And you see few systems have all analytical eigenstates to test the completeness. Use Parking box as an example to demonstrate completeness of eigenstates. And this completeness, which means this is kind of strange. And this is also, I think I like this example so much. This is called completeness. Complete means the following. And if you notice the wave function star, wave function n, like this. And here your variable x. Here's the variable x. If you look at the standard textbook, they will tell the students, okay, students, let's look at how we do the calculation. Sum over n. Remember, this is sum over n, not sum over x. Did you sum over x like interval that I didn't know? It's sum over n, and it said this equals 1. When I was learning quantum mechanics, I found this is the most abstract concept. Cody, did you find something strange? This is a constant. But here we have x variable. Did you see the problem there? You know, if this is a constant, I could agree with you, no problem with that. But this has an x in it. If I change the x, you look at this is the wave function. If I change x, how in the world do you get a 1? It's just conceptually doesn't make a lot of sense to me. Even though I read textbook, I still seems to be understand it, sum over this. So then I would try to see whether I can find an equation, break down this completeness. It turns out I failed. Why? When I sum over this, now there's two things involved. I'm going to show you one here. This is location 1, not means the location number 1. Here's the location number 2. Two locations are very important. Question number 1. Do we have a factor here? In other words, could you guys write this down? In other words, we put a 1 in the front. Do we have a factor in front? Because if you look at all the books, they just sum over like this. They didn't tell you anything about this. Second, the second point, how many states should we include? So we have two questions, Cody. You see that. Do we have anything in the front? How many states we do need to include? And when we are writing this, when we're writing this book, and I was so baffled because I have a computer, I can do a whole bunch of things calculation. It turns out, if you look at the equation 2.3.15, did you see that? 2.3.15, did you see that equation? Did you see that? Did you see that? Did you see? It has to be A divided by N. And this is astonishing. No textbook ever mentioned this. This A, this 1 here, must be A over N. If you simply divide by N, you never end up with the 1. So you have to multiply by A. Where is A? Well, this guy is A here. This is A. I do not understand why in the world we have to multiply by A. If you didn't multiply A, you won't get equal to 1. So that's it. Did I answer your question very well? It should be A over N. That's the base factor in front. How many states we have? For the particle box, I use letter P, I, B. And if you look at our figure 2.2, that's figure 2.2. This is the completeness eigenstates tested with A equals 10. The figure uses the code completeness in the appendix 11.1. This is the first code which we will do on Wednesday. Did you see if I use a 10 state, this is the black curve, 10 state. Did you see it's wiggling, oscillating so much? Did you see that? Also, so much oscillating, but it's around 1 like this. Now I keep on increasing 20, it still has some oscillation. Once I include to 300, now you see the line, straight line comes out. And you never see a book actually show this figure. And I was thinking, if you think completeness is so important, but why don't you show us a figure like this? No book has this. So I'm so glad that I at least, I think we figured out, you must multiply by A in the front. If you simply divide by this, it won't work. I tested in the test, that doesn't work. So you must multiply by A. So the larger the A, this whole thing will be larger. So, and the main reason, of course, you understand very well. Why I multiply by A. So I also understand. This is part knowledge 3. We will ask you on Wednesday. Why we need to multiply A? That's a 3. So we will ask you. Why do we do that? The main reason is, if you look at my wave function, do you see wave function times each other? If you multiply by each other, you'll get 2 over A. Did you see? If you multiply by each other, you get a 2 over A. If you did not multiply by A, these 2A cannot be cancelled out. These 2 A's cannot be cancelled out. You know, if you use a larger A versus smaller A's, if you did not cancel them out, won't be there. So therefore, you see this one 1A, this A, and this A, they cancel out. So that's why it becomes like this. Because you tell the student you need to normalize the wave function, but yourself will never use it. Here I use it. And on Wednesday, when you will log into the HPC, and you can see for yourself, you can test how many states you want. You will gradually see the curve like that. Sounds good? End of class. And so, any questions before I shut down? No questions? Wednesday we have a quiz, so make sure get ready for that. This is essentially a makeup quiz for last week because I'm really not satisfied with your answer. What is a quantum? I'm still handing my mind. Okay. See you guys. All right. Okay, I'm good.